So, Baram, how are you?
I'm good. Thank you.
Thanks to you for joining us and for the wait. So, if you are ready, so without any further delays, so it is a pleasure to to introduce Param Singh from the Department of Physics and Astronomy of the Louisiana State University, and he's going to tell us about quantum gravitational onset of Starobinsky inflation in a closed universe. So enjoy the talk.
Okay, thank you very much, Gonzalo. I really wish to thank Gonzalo and other organizers for asking me to give a talk. It is my great pleasure. What I'm going to talk about is first some sort of an overview of what is an approach from quantum gravity called loop quantum cosmology. I know probably most of you have not heard about it, though Gonzalo has worked on it on a very seminal paper long time back, and Adria and Gonzalo and I have been working on another project right now. But just for the students and postdocs who are not aware of this approach, I would give an overview of the approach without going into too much technical details. And then what I will do is I will apply this approach to what I see as a very important problem, which is right now in early universe cosmology, which is how to start Starobinsky inflation in a closed universe. So just to mention that the recent Planck data, it has been favoring Starobinsky inflationary model for now quite some time. And the recent data also slightly favors a spatially closed universe. So I will point out what are the issues in the classical cosmology and even starting this inflation, which have been pointed out originally by Andre Linde many years ago. And we will see like how quantum gravity effects can help in setting the right initial conditions for this inflation to start. This work is essentially based on 3 papers, like John Dupe was my undergrad student, Lucia Gordon was also my undergrad student, and Dr. Lee is my postdoc, and Mei Sum is my PhD student, and I will be giving some results from these papers. Okay, so I will first give an overview, and in the middle I will also start talking about some of the things which are relevant for this particular problem at hand. So the outline of the talk is, first I will discuss the problem of singularities, which we are all very well aware of, which are of the Big Bang and Big Crunch. Then I will discuss early attempts in quantum cosmology to solve these problems. And with these early attempts, I mean Wheeler-DeWitt quantum cosmology. And we will see how this Wheeler-DeWitt quantum cosmology really does not address the issue of cosmological singularities. Then I will come to loop quantum cosmology, and I will give an overview of main results. Loop quantum cosmology is essentially a framework of doing quantum cosmology motivated by techniques of loop quantum gravity. And then we will use this loop quantum cosmology, or LQC, to understand the onset of Starobinsky inflation in closed universe. And then I'll summarize with the main results. Okay, so we all know that though Einstein's theory of general relativity is extremely successful in describing our universe from very early times till now, it really fails when the space-time curvature becomes Planckian. The fundamental questions about the birth of our universe, especially like how the initial conditions were set for the very early universe, they are not possible to answer many times without overcoming singularities. And if we want to understand how to resolve singularities, I think it is a good idea to first define what we mean by singularities. What I will mean by singularities in this talk will be space-like singularities. There are various ways you can quantify these singularities, and some of the features of these singularities are that the space-time curvature, the energy density, the space-time shear or the anisotropic shear, the tidal forces, they become infinite when you reach these singularities. Now there are various ways, like not all singularities share these features. So therefore, in 1970s and 80s, a lot of work was done to quantify different kinds of singularities, and they were classified as strong singularities and weak singularities. Strong singularities are essentially those singularities that, irrespective of how strong a detector or an apparatus you make and you throw it towards a singularity, the tidal forces are so strong or infinite that the detector will essentially break apart and the singularity will be met. A weak singularity, on the other hand, is a kind of singularity which in principle you can escape. That maybe a one component of the space-time curvature is diverging, but the tidal forces are not infinite in various cases, and you can in principle make a strong enough detector which can survive the singularity. So the weak singularities are not viewed as the boundaries of space-time because you can in principle go through them, or even if you encounter them, there are ways to maximally extend the space-time and then go through them. The strong singularities are really the boundaries of the validity of the classical space-time, and these are the singularities which we would like to attack. Simple examples of these strong singularities are the Big Bang and the Big Crunch singularities, which we'll encounter in this talk. Also, like the Schwarzschild interior has a strong singularity. Now, interestingly, singularities like in 1940s were thought to be artifacts of simplifying assumptions. Eddington and Tolman thought in 1940s that the singularities like Big Bang would essentially go away because the moment you will include anisotropies, first to mention, these were found in the very simple systems. Homogeneous and isotropic spacetimes were the models which were studied in which these Big Bang singularities were found. And Eddington and Tolman, who were great defenders of Einstein's theory, they said that, well, Einstein's theory has essentially no problem. These models are extremely simple. That is why they are having these singularities. The moment you will put anisotropies, the moment you will put inhomogeneities, these singularities will just go away. But it turned out to be false. It was shown by Rai Chaudhuri in 1955 that if you include anisotropies, singularities are still present. And then famous works of Roger Penrose and Stephen Hawking showed that in presence of inhomogeneities, singularities are very generic results. So we have to live with the singularities in GR. They are the essential deficiencies of GR which motivate us to go beyond GR and look for a quantum theory of gravity. Okay, now let us come to some questions. If we want to resolve singularities, there are some questions we can ask. First of all, is Big Bang singularity in cosmology, is it an artifact of assuming a classical space-time continuum at all scales? Maybe if we give away this assumption that there is a classical space-time differentiable manifold at all scales, maybe the singularity will get resolved. Now we cannot put this such an alternative by hand. A theory has to give us an alternative, and then we'll have to work with the implications of that alternative. One such theory can be quantum theory of space-time itself. Like maybe we have to quantize the space and time itself to get a quantum theory of gravity, which resolves a Big Bang and Big Crunch singularity. Now, different experts have different ways to think about this problem. String theorists will probably not say that we need a quantum theory of space. People working in modified theory of gravity would also probably not say that. They will say like probably we need higher order actions and so on. But in my view, these approaches essentially are trying to attack the same problem from different angles, and they would converge at some point. The main question is, if there is a quantum theory of space-time or quantum theory of gravity, which is the view taken in loop quantum gravity, then what replaces the Big Bang and Big Crunch? And there have been essentially two kinds of ideas. If we look carefully in the literature, two kinds of ideas have been the prominent ones, and things have gravitated towards these two kinds of ideas. The first idea essentially is pretty old, and if you look into mythology or ancient philosophy or string-inspired scenarios or more recent scenarios like matter-bound scenarios and so on, the main paradigm is that the universe is classical on the other side, the singularity will be resolved, and the universe will be classical on the other side, which might have some properties similar to ours. That's a question we have to understand. Is the universe having similar properties like ours on the other side? The second idea, essentially, also very powerful idea, was essentially first given by Wheeler, that as one will approach these cosmological or black hole singularities, the quantum fluctuations will become so strong that the whole nature of metric will disappear, and the space-time will just become like a quantum form. We won't be able to describe the space-time around these singularities or beyond these singularities. Now, which of these ideas is true? strongly depends on what paradigm one is working with, what is underlying theory, and what are the predictions of the theory. In loop quantum cosmology, we do not make any assumptions on which one of these statements is true. We quantize the theory, we do numerical simulations, and then we figure out whether one of them is true or not. And I will come to those results, and these results will be helpful for us to understand the problem I want to address in today's talk. Okay, but whenever I give a talk like this, like one of the very important questions which come from young students especially is that, well, we have been working on quantum gravity for last 80 years, and why we do not have a theory of quantum gravity. And I think in this small brief slide, I would like to emphasize what is essentially the main point and why we do not have a theory of quantum gravity yet, a full theory of quantum gravity yet, and what is essentially the philosophy of loop quantum gravity in particular. The main message, if we take one-line message, one sentence message from general relativity, is that the general relativity describes as the dynamics of space-time. That is the paradigm change from Newtonian gravity. And the gravitational interactions are fundamentally different from other interactions. Gravity is nothing but just the bending of the space-time. We all know that. It's a dynamical feature of the space-time. On the other hand, the quantum theory tells us that the microscopic world is very different from the macroscopic world. And all dynamical fields, whichever you are physically interested in, must be quantized. Now, if you are looking for a marriage of these two ideas, then it essentially means that you have to quantize the dynamics of the space-time, or you have to quantize the dynamical space-time. Now, how do we quantize this dynamical space-time? Whenever we have learned about QED or QFT or electroweak theory, space-time is given to us, and then we construct operators and objects on it to quantize those material fields. But now if we have to quantize the dynamical space-time itself, it's an extremely hard problem, both at conceptual level and technical level. And the situation becomes worse because there is no observational input, at least direct observational input, to guide the theory. So it's not that any theory can be just postulated. That is why there are extremely few candidates of quantum gravity in literature. The theory is essentially relying on self-consistency, self-mathematical consistency, and there are cross-checks at each stage for simplified models and so on to see whether we are going in the right direction or not. Okay, so with this small introduction, let us come to cosmological models, and let us try to see some simple singularities before we go back into quantum cosmology. So I just want to give you a very small introduction on what kind of singularities we are going to see. So I'm going to take a spatially flat homogeneous and isotropic space-time FLRW model, which is spatially flat right now. Then I'm going to go to closed universes, in which the metric is given by ds square equals minus dt square. I'm taking the lapse equal to 1 plus a square dx square, and a square denotes a scale factor. Now, using Einstein field equations, we can get the Friedmann equation, which is 8 pi j a Hubble square, which is a dot square by a square equals 8 pi j rho by 3, and the Raychaudhuri equation, which is a double dot by a, which is minus 4 pi g by 3 rho plus 3p. Okay, rho is the energy density and p is the pressure of the matter field. Now, suppose you have dust. In the case of dust, the pressure is 0 and the energy density goes as 1 over a cube. And then we can easily see that the space-time curvature becomes infinite as the scale factor goes to 0. And this is the Big Bang singularity, which will be reached in the finite time. Now, interestingly, what happens is that even if you have an inflationary space-time, an inflationary space-time is characterized by when the energy density becomes equals to minus of pressure. Sorry, there is a p should be small here. Then even then the Big Bang singularity exists. The only way to avoid the Big Bang singularity in such simple models is you have to introduce some very exotic matter which violates the weak energy condition, such as a phantom field which has negative kinetic energy. This is for the isotropic case. So in the isotropic case, it is easy to see that for all matter which satisfies the null energy condition, there will be a Big Bang singularity in past. If you have an isotropies, then this Friedmann equation gets modified with an addition of an anisotropic term, which goes as sigma square. And this sigma square, it scales as 1 over A6, always. It goes as 1 over A6. That is a property of the anisotropic shear. So what happens is that irrespective of what matter you put in, except a massless scalar field or just the kinetic energy term, which goes as 1 over A6, the Friedmann equation and the Raychaudhuri equation correspondingly, their evolution, the evolution generated is such that the anisotropies determine the singularity structure. So it is very important to remember that whenever anisotropies are present, the picture which we generally have in mind of the Big Bang being a point is not true. It's a very special case. The Big Bang generally is like a cigar or like a pancake or like a barrel, and these singularities have been discussed a lot in 1970s and 80s. A lot of work has been done to understand the geometry of these singularities when the anisotropies are present. Our interest in this work, in this talk, is not on the spatially flat model, where we will use spatially flat model to gain insights, but our interest is in spatially closed model. So let us see what happens in a spatially closed model. In the spatially closed model, the Friedmann equation changes to this particular form with minus 1 over A square as the term which comes from intrinsic curvature. Now this term plays a very important role, and this, we will see, this term is going to cause lots of difficulties for inflation to start. So what happens is that if, first of all, we should notice that the energy density, which is proportional to a to the power minus 3 1 plus W, where W is the equation of state of matter. Equation of state is defined as pressure divided by the energy density. So for example, if you have equation of state equal to 0, then that is the energy density of dust, which goes as a to the power minus 3. If you have equation of state equals 1 over 3, which is of radiation, then it goes as a to the power minus 4. If you have equation of state as minus 1, which is like in a de Sitter evolution or slow roll evolution, then energy density is constant. And if you have equation of state of 1, which is for the massless scalar field, for example, or just when you have a scalar field in which just you have the kinetic energy, then the energy density goes as a to the power minus 6. Now, imagine a situation when the energy density is going as a to the power minus 6, which is a field without a potential. And then in that case, this term, the first term, 8 pi g rho by 3, as the universe will expand, will start expanding, let us say from Big Bang, then this term will decay extremely quickly compared to the spatial curvature term. And eventually what will happen is that the spatial curvature term, even if the spatial curvature term is small in the beginning, it will catch up with the first term, because the first term is decaying very fast. It will catch up, these two terms will cancel each other, and the Hubble rate will become 0. When the Hubble rate becomes 0, one can show from the Raychaudhuri equation that it corresponds in this case to a recollapse of the universe. The universe starts expanding, but very quickly the universe reaches the maximum size and it starts contracting back. And once the universe starts contracting back, this term, the first term, starts winning again, because it is going as 1 over A6 for a kinetic energy dominated field, and then this term quickly grows, and as it quickly grows, the universe reaches the singularity A equal to 0 with this term, energy density diverging, Hubble rate diverging, space-time curvature diverging. So what happens is essentially that in the spatially closed universes, it can very well occur that the spatial curvature can cause a recollapse of the universe unless the energy density dominates. Now this energy density, that means that has to dominate. But if it does not dominate, there will be a recollapse of the universe, and after the recollapse, there is going to be a big crunch singularity, and the universe will just end its evolution. Let us now see what happens if you have. How do you avoid this phase of recollapse? The only way to avoid this phase is, as we can see, this term is, the second term is going as 1 over A square. So the first term also has to go at least as 1 over A square, or better than that. And that means you need an equation of state W, which is less than minus 1 by 3. And it is easy to check from the Raychaudhuri equation that this means accelerated expansion. This means A double dot by A is greater than 0. And this is the necessary condition for inflation to occur. Inflation essentially means that W is less than -1/3. Now, in various models, W is equal to -1 or close to -1. So that is much better than this scenario. So the main message is, in the case of a spatially closed universe, the things quickly get complicated. And if you have a universe which is inflationary to begin with, suppose you give the initial conditions of the universe such that the universe enters into accelerated expansion very quickly, then such a universe can overcome the attraction because of the spatial curvature and can inflate. But if the universe takes some time to get into the stage of inflation and so on, then it is highly unlikely that the universe will be able to overcome the spatial curvature before the recollapse occurs. And once the recollapse occurs, there is no going back. The universe is going to get into the Big Crunch singularity. So this is an issue. This is the main issue which we want to look into this talk. If the initial conditions of a closed universe are set in a Planck era, if you start from the Planck era, then whether or not inflation starts is very much tied to the potential. That is the main thing. So let us take the case of a very popular model till recently, which was phi-square inflation. And this was the favorite model of most of the cosmologists. And for the chaotic inflationary scenario, the phi-square inflation, the model is such that the initial conditions of the inflaton, when you start from the single Planck size domain in the very early universe, can be such that the potential energy dominates and the universe enters into inflationary phase before recollapse can occur. Let me just explain a bit more. So when you give the initial conditions on the Planck size domain, when this chaotic inflation is, or these bubbles of the universe are just starting, then the phi-square inflation model has no restrictions on what should be the ratio of the kinetic and potential energy. The potential energy can be of the order of Planck density itself, in principle. And then once you have such a high potential energy, what happens is that if you look at this first equation, then this rho is actually acting with an equation state close to -1, and such a bubble just pops out and starts expanding and inflating. If this will be the most favorable initial condition. But even if you have some moderately favorable initial conditions in which there is some kinetic energy of the field is not slowly rolling, some potential energy of the field, then the ratio can be such that this equation of state is not far from this -1/3. And then the inflation can start in just few Planck seconds, such as to overcome this -1/a² term, and it can inflate. Now you may say, well, these are still fine-tuned initial conditions. Yes, they are. You can choose initial conditions which are highly unfavorable. You can say, well, I do not want my field to be slowly rolling when the universe started at the on this Planck size domain. There is a multiverse, and there are plethora of initial conditions which are possible. Yes, that is true. And you can start from kinetic energy dominated field. And in that case, there will be problems. In that case, it is not guaranteed that the inflation is going to start. In that case, the field will cause the universe to expand a bit. But if its potential energy does not catch up, then the universe will again see a recollapse and get into Big Crunch. So it is not guaranteed. The important thing is to understand that it is not guaranteed, even for the chaotic inflationary scenario, for the inflation to start in the closed universe. But there exist a lot of initial conditions such that inflation can start. The situation changes completely for models like Starobinsky potential, which is right now the most popular model. These are low energy inflationary models. What it means is that the inflation actually starts not at the Planck density, but the inflation, you can give initial conditions in the Planck regime, but the inflation starts 10 to the power minus 10, 10 to the power minus 12 orders below the Planck density. That's a very bad news, because what it means is that the kinetic energy dominates for a very long time in these potentials when you start from the initial conditions. And if the kinetic energy dominates, we know what will happen. This rho, then in that case, the energy density will go as 8 to the power minus 6, because the field will behave like massless scalar field. The energy density will go as 8 to the power minus 6. And then this will inevitably cause a recollapse of the universe. So the main message is chaotic inflationary scenarios are very favorable. You can have favorable initial conditions for inflation to start, even if the universe is closed. But for Starobinsky potential, conditions are highly unfavorable. And this is without any doubt was the main statement by Linde for a very long time. And he has put that in his monograph and his reviews and so on, that for Starobinsky potential, the closed universes end. If the Starobinsky potential is there, and if you want to start inflation in that, closed universes end within few Planck seconds, and it is highly unlikely that inflation starts. Because there is a recollapse and there is a big crunch, inflation doesn't even begin. And that was one of his main arguments to favor 5-scale inflationary potentials. Whenever there was a compare and contrast between 5-scale inflationary models or 5-4 inflationary models with low energy inflationary models, then this was one of the main arguments that in quantum cosmology, we generally start from a closed universe. And if you want to look at the probabilities for the inflation to start, the probability for the inflation to start in low energy inflationary models is extremely low. This was all fine till the Planck data started favoring the Starobinsky potential. Now, but more recently, the Planck data favors a spatially closed universe with a low energy scale inflationary potential such as Starobinsky potential. So the problem which was just theoretical in nature or just for academic understanding has now become an important problem, because we would like to really solve this problem, that if the data is favoring such scenarios, then how do we start the inflation in such scenarios? So the main thing I would like to talk about is, can quantum gravity effects result in resolution of the big crunch singularity? Suppose there is a quantum gravity effect which resolves a big crunch singularity. Then you may think, okay, now there will be some sort of a bounce, and there can be bounces and so on. But can such bounces lead to viable initial conditions for Starobinsky inflation? The answer is not obvious, because even if a model resolves a singularity, it may mean nothing, because the universe may be just cycling symmetrically from one cycle to another. What it means is that the kinetic and the potential energy ratio may remain the same in one cycle to another, and the universe may go into endless cycles without inflation to start. One needs something more, and that has to come from the dynamics itself, and that is that the non-singular evolution must be asymmetrical. It should not be symmetrical. It should be asymmetrical in such a way that it causes the potential energy to dominate in subsequent cycles and inflation to start. And this is what we will see would happen with the quantum cosmology effects. Okay, so now I'm again going to go back to quantum cosmology. I have given the main motivation of the talk and the framework we are going to be working in. So I'm going to go back into the same overview to show how quantum cosmology resolves the singularities, and then we will come back to these closed universes. So I view quantum cosmology essentially as a kindergarten for quantum gravity. It's like a primary school in which you can learn lots of things, but still not master the quantum gravity, but still extremely important to eventually master the subject. Why is that the case? Because cosmological spacetimes have enormous symmetries. If you're working with FLRW spacetimes, they're homogeneous and they're isotropic. And that means one is working with finite degrees of freedom. And we know our universe is homogeneous and isotropic. And further, we also know from studies in classical GR that the singularity structure is not really determined by inhomogeneities. Singularity structure is determined more by anisotropies. Even if you include anisotropies, the degrees of freedom remain finite. From 2 degrees of freedom, you may get few more degrees of freedom, but the degrees of freedom are still finite. So the nice thing is that once you assume homogeneity of the space-time and you work with isotropic and anisotropic models, then various hurdles of the full quantum gravity can be bypassed. Many of these technical hurdles arise because of these infinite degrees of freedom. It allows a complete quantization of various interesting and non-trivial spacetimes, and that complete quantization has been accomplished successfully in the last 15 years. Essentially, the main thing is we are not doing quantum field theory of spacetime. We are not doing quantum field theory of quantum spacetime. Okay, first of all, we do not have a classical spacetime. We have a quantum spacetime, but we are not doing quantum field theory on that. That is the full loop quantum gravity, or that will be like string theory and so on. What we are doing is, on this quantum spacetime, we are understanding the quantum mechanics of gravity. We are not doing QFT. Obviously, quantum mechanics does not fully capture all the aspects of quantum field theory. But it is also true that many of the main results, they are not so different between the two theories. It gives us a lot of intuition on even how to do quantum field theory. So quantum cosmology therefore serves as a testing ground to develop new techniques for quantum gravity. And the idea is of the people doing quantum cosmology is that perhaps it can alleviate some of the problems in the early universe cosmology too. And various people have been working on how to connect these quantum gravity with observations using quantum cosmology. And I would state a very important caveat that all the results which I'm going to discuss must be taken with a lot of caution. Essentially, we are doing like quantum mechanics on this quantum space-time. We are not doing QFT on quantum space-time. The hope is that the qualitative results would survive and one can learn important lessons. So let me tell you how the machinery works. So this is a very simple model, homogeneous and isotropic universe with a massless scalar field. You write it in the canonical description, and then you identify the Hamilton's equations and the Hamiltonian. So the matter Hamiltonian in this case is given by p phi squared by 2v. It's a massless scalar field. P phi is the field momentum, v is the volume of the universe, which is the cube of the scale factor. And the Hamilton's equations yield that the p phi, the momentum of the field, is a constant, and phi goes as log of v. Phi here serves as a clock. Many of you must have heard about the problem of time in quantum gravity, and what quantum cosmology people also do is we try to resolve the problem of time in a way by introducing some sort of a matter clock as an example. So what we can do is we can take phi as a clock which measures the way the scale factor or the geometry changes with matter. And in the classical, if you're doing classical canonical cosmology or classical Hamiltonian cosmology, then you'll find two solutions for this particular model. Only two solutions for a given value of p phi. An expanding branch, which is the upper branch in this plot below, and the contracting branch, which is the lower branch in the plot below. So phi is the time. As the phi increases in the expanding branch, the universe expands. As the phi decreases in the contracting branch, as the phi moves forward, the universe goes to a big crunch. So here there is a Big Bang singularity, and here there is a Big Crunch singularity. Important thing is these two solutions are disjoint. These two solutions do not talk to each other. And now what we would like to do is we would like to quantize it. So the idea of Wheeler-DeWitt, which was in 1970s, the Wheeler-DeWitt quantum cosmology was essentially to treat this system as a classical system on a phase space and quantize using the methods which Heisenberg and Dirac have given us. So one identifies the phase space variables. The basic variables are the volume and the conjugate of the volume, which is the kind of the extrinsic curvature, which is v dot, proportional to v dot. They are the geometrical degrees of freedom, and the matter, which is phi, and p phi, which are the matter degrees of freedom. And then, as in quantum mechanics, we elevate them to operators on a suitably defined Hilbert space, and we look at the Hamiltonian of this system. So this is essentially like the quantum gravitational Schrodinger equation in the blue. And I'm not right now here worrying about factor ordering ambiguities, but I'm writing it in a simple form. The gravitational part acting on psi, which depends on the volume and the phi. So the phi serves as time, equal to the matter part acting on this side. If you have a massless scalar, this equation becomes extremely simple. And this equation just becomes the second order differential equation, where alpha is log of v. And this is a quantum theory you can easily solve. You can write down the observables. You can use the inner product, which is available, the Klein-Gordon inner product, or even the Schrodinger inner product. And then what you can do is you can choose your wave function as a sharply peaked state. Let us say today, in a large classical macroscopic universe, I can choose a sharply peaked state peaked on Einstein's trajectory, the trajectory from Einstein's theory of general relativity. And I can evolve this state backwards towards the Big Bang. And then I can hope to see whether the singularity is resolved or not. So I can use this equation as an evolution equation with phi as time to understand how alpha, which is log of v, changes. And then I can compare with general relativity, and then I can extract the predictions for the theory. Unfortunately, what happens is that if you do this exercise, so if I take a state at very large volumes, so this is all in Planck units, I'm plotting the magnitude of the wave function on the z-axis, the volume on this axis, and the phi is being measured here. If I take this state and if I evolve it backwards towards the Big Bang, then unfortunately this state in the Wheeler-DeWitt theory keeps following the classical trajectory all the way into the Big Bang and ends into the Big Bang. The singularity is not resolved. So essentially what happens is that if you take the state on the classical trajectory, let us say the expanding trajectory, and you go backwards, the state goes into the Big Bang directly. If you take the state on the contracting trajectory and you go forward, you will reach into the Big Crunch singularity. Somebody might think, well, maybe I can take a superposition of the states. In the quantum theory, superpositions are allowed. Let me take the superpositions of the states on the expanding and the contracting trajectory, and maybe I will resolve the singularity. It turns out that also doesn't happen. For arbitrary superpositions, we have shown in the Wheeler-DeWitt theory, and this is the work with David Craig I did some years back, using consistent histories formalism given by Hartle and Halliwell. If you take arbitrary superpositions of states in the Wheeler-DeWitt theory, and you evolve them towards a singularity, even then the probability of singularity is exactly 1 in infinite time. So there is no way the singularity can be resolved for this particular model. Yes, you can introduce a potential and you can fine-tune the conditions for the potential, and you can choose very fine-tuned initial conditions such that singularities may be resolved in very special conditions. But those exact analogies also occur in the classical cosmology. We are not looking for fine-tuned initial conditions or exotic matter to solve singularities. We want to see how quantum gravity can resolve them robustly. The main reason I feel the singularity is not resolved in Wheeler-DeWitt theory is because the properties of the space-time are same as in the classical theory. The Wheeler-DeWitt equation I showed you here is a differential equation on a differentiable manifold. It has no quantum properties in this manifold. And if the singularities were occurring essentially because of dividing the space and time to smaller and smaller sizes, then there is no way that Wheeler-DeWitt equation is going to resolve the singularity, at least robustly. Secondly, this was in some sense like an independent scenario which was not guided from a full theory of quantum gravity, any underlying full theory of quantum gravity, which can tell, well, these are the things which we have to do to resolve or to quantize the model. So let's go beyond now. These were the early attempts in quantum cosmology, and we have looked at these attempts again in recent years, and we didn't find singularity resolution occurring. So now let me come to loop quantum gravity and cosmology, and I'm going to give an extremely unfair treatment by just putting everything in the one slide to make it as non-technical as possible. The main message of loop quantum gravity is that it's similar to canonical quantization, which was envisioned in the Wheeler-DeWitt quantum gravity, but it's a non-perturbative quantization of space-time based on new variables, which are very similar to electromagnetism. New variables are the connection, also called as the Ashtager-Barbero connection, which is analogous to the vector potential in electromagnetism, and the triad, which is analogous to the electric field. At least kinematically, the loop quantum gravity is on the same footing as the electroweak theory because it has similar vector potential and similar electric field. Now, as I was mentioning, it's an extremely hard exercise because unlike other theories, there is no space-time given to us. Everything is very abstract. And thanks to like a lot of seminal work by various people mentioned here, a very high mathematical precision was achieved in 90s. The main message from these results was that at least at the kinematical level, the classical differential geometry of GR is replaced by quantum discrete geometry. And then a very nice result followed about 15 years ago, that at least at the kinematical level, there's a uniqueness of the quantum theory. So when I was a postdoc at Penn State with Ashtager and with my friend Tomek Pawlowski, who is in Warsaw now, we started looking at this construction of loop quantum gravity as applied to cosmology in some more detail, some more rigorously. There were earlier works coming from Martin Boyeward, and those works were very promising, but there were certain gaps, and we were aiming to fill those gaps and to try to construct a rigorous quantum theory of this field. So what we found is that you can indeed achieve the full loop quantization as was envisioned in the loop quantum gravity program for homogeneous and isotropic spacetimes we were able to find a complete quantization. And what we found is that instead of that differential equation, which I showed you for Wheeler-DeWitt spacetime, if you follow the loop quantum gravity program, you get a difference equation. You do not get a differential equation. The reason you get a difference equation is essentially tied to the fact that if you look at the area operator in loop quantum gravity, then it has discrete eigenvalues with a non-zero minimum eigenvalue. So this difference equation essentially has uniform steps in volume. I'm not showing what is C plus, C0, C minus. They are not very useful to be shown. Some complicated functions of the volume and the spacings of the volume and so on. But the essential part was in loop quantum gravity, the left-hand side, the gravity side, gets discretized automatically, not put in by hand, just because the area is there in loop quantum gravity. Whereas the right-hand side remains the same. It remains the same as in the other models. So what are the consequences of this different equation? The consequences were very striking. If we took a state, and if we evolve it backwards, exactly as with the same initial conditions as the Wheeler-DeWitt quantum cosmology, same. If you evolve it backward, but you use the difference equation now, then what happens is that state turns around. It bounces from the expanding branch to the contracting branch, or from the contracting branch to the expanding branch. Recall that there were two branches. I showed you the expanding and the contracting branches. They were disjoint. And the miraculous thing that happens is that the state follows the expanding branch for a very long time if you are rewinding the movie of the universe. And very close to the Planck density, like 0.4, the value of the Planck density, the state switches from one branch to another in a very smooth and in a very non-singular way. The state remains sharply peaked throughout. So this is exactly like what was the picture also in some string theoretic models, that the universe, there will be a bounce, which is found here, and before the bounce, your universe retains many of its classical properties. And this is the artistic impression that the space-time is classical on one side, and as you approach the Big Bang, there is a bridge, and the space-time is classical on the other side. And what we found is that the states which are sharply peaked at late times, the Big Bang singularity is replaced by a quantum bounce at a maximum of energy density. And this maximum of energy density we first found using numerical simulations. Later we found analytically from the expectation values of the Hilbert space and so on. It always turns out to be 0.41 times the Planck density. There is no free parameter here. Everything is determined here by the loop quantum gravity itself. Okay, now what happens in the closed model? We studied the closed model, the full quantum theory of it. The closed model has its own challenges. The challenges are that not only the Big Bang singularity has to be resolved, but the Big Crunch singularity also has to be resolved. But not only that, if your theory is consistent, like one question which is generally asked, which sometimes is I've seen in forums saying, well, loop quantum gravity does not give you GR at low energy scales. This figure shows you that that is completely absurd assertion. If the theory gives you the right infrared limit, then what it means is that if there is a recollapse occurring at large scale factors at very late times, then the theory will give you the recollapse at exactly the same scale factor. And we see here, you start the universe, let us say, from some phi equals -5. And these are in some clock phi. Again, you can choose phi as a clock. The universe starts in a way that it sees a Big Crunch singularity, and the universe bounces because of, this is the loop quantum cosmology picture, and you cannot see, but there is a green curve which shows the classical universe, which goes into the Big Crunch singularity. There is also an effective curve, and this an effective curve is an effective space-time description of loop quantum cosmology. So let us just focus on the red curve right now. So the red curve shows that these expectation values computed, the universe avoids the Big Crunch, expands again, and then it again recollapses, as it would recollapse in the classical theory. It would recollapse and go back again towards the Big Crunch. And see the green curve and the red curve, they are essentially just matching. So the theory predicts recollapse exactly at the same point where the classical theory wants a recollapse. So it has a right infrared limit. Also, it has a good ultraviolet limit, because it is avoiding the singularities. Now you cannot see the effective curve essentially because the effective curve lies exactly at the center of the points within these error bars, which are the fluctuations of the red curve, which shows that the effective trajectory is extremely good in describing the non-singular evolution from the Big Bang to Big Crunch and so on through different cycles. And we did this simulation for about a year, and we did this simulation not for just few hundred or few thousand cycles, but about 1 million cycles. And we didn't see any change occurring either in the recollapse point or the bounce point and so on, showing that the state preserves its semi-classical properties very nicely when it goes from the bounce to avoiding Big Crunch and going through recollapse and so on, providing a very accurate test, I would say, of the recovery of GR from loop quantum cosmology. So this built us like an intuition about the spatially closed universe. And in the last 1.5 decade, or last decade, various groups all over the world have generalized these results and taken them forward in various directions. I'm just pointing out some of the groups which have remained with a lot of activity. Various very rich physics is being explored using effective spacetime, including in the Valencia group, which has played a very important role in establishing a very important result early on. And signatures in cosmological perturbations are now being pursued by different groups throughout the world. And these same techniques are now being applied to black hole spacetimes. These are, I would still say, these are preliminary works, but the results are very strong that the singularities are being resolved in the Schwarzschild black holes. Okay, so with this introduction, now we are having a good background, and I will now try to tell you the main results about the Starobinsky inflation. So let us go back to the Starobinsky inflation case and the closed universe case. So the main question is how LQC helps in the onset of inflation. So let us see that. So for the spatially closed model, presence of a phi-square inflationary potential. Suppose I start from highly unfavorable initial conditions. Suppose I do not want to consider the universe which is so fine-tuned that I start just from the potential energy domination and the inflation just starts. In a multiverse kind of a scenario, like you will have kinetic energy domination also. So if you start, and I will call them as highly unfavorable, which are just purely kinetic energy dominated conditions. For such initial conditions, we know that there will be a bounce, there will be a recollapse, and in the classical theory, there will be a big crunch. What happens in loop quantum cosmology is the following, which is shown in the figure. So I start from a universe which is 10 to the power 6 some in the volume, so it's still a small universe. It's like just 100 times the Planck length in scale factor, and I take the contracting. I start from highly unfavorable conditions. I just force it. Okay, the universe should just contract and go towards the big crunch. In the classical theory, the universe will end at this red curve. Now I'm showing you the red curve and the blue curve. The reason is because, as in different quantum theories, there are certain quantization ambiguities, and this exercise was done for 2 different models in loop quantum cosmology itself, and both the models show the similar evolution with slight differences. So what one finds is, so you can just focus on one curve, red or blue, and that will get the main message. The point is that one starts from some universe which is 100 times bigger than Planck length and forces it towards the contraction, highly unfavorable initial conditions. One finds that loop quantum cosmology causes a bounce, recollapse, bounce, recollapse, bounce, recollapse, and so on. A very interesting thing happens. If these bounces and recollapses were such that the maxima of the recollapse is not increasing, then we are doomed. Then what would have happened is that these bounces and recollapses will keep on cycling infinite number of times, and nothing really wonderful will happen. But what we found, and this was the work which I did with John Dupuy recently, we found that in each cycle, the maximum of the cycle increases. And if you compute the work done, actually, the integral of PdV, if you look at the wave equation of state changes, then you find that gravity is doing some non-zero work and putting that, and it's pumping the field slowly up, even though the potential is such that the field is at the bottom of the potential. In each cycle acts like a small little pump, like you pump the bicycles. If you have a deflated tire, each cycle acts like a pump till the tire completely inflates. And that is what happens. Each cycle causes a pumping, and a pumping is slow, but it's still there. And eventually what happens is that a sufficient pumping occurs that the field starts inflating. Why does it occur? Because in each cycle, the field starts going up the potential slowly and slowly. Eventually it reaches a height enough that it just falls down because of gravity, essentially because of the way it occurs in slow run inflation, and then inflation starts. So let us see it more quantitatively. The right way to look at it is the equation of state. We look at equation of state versus time. This is for the same simulation. Since in each cycle the potential energy of the field increases, slowly the equation of state, even though you start from unity, decreases. So I started from the kinetic energy domination. So the W is 1 because the field is just massless. And in each cycle, the equation of state at the recollapse points starts decreasing. It starts from 1, but keeps on decreasing. And eventually, a push comes in one cycle that it crosses -1/3. If you see a small bend here, it crosses -1/3. And as we saw earlier, that is the condition you need. If the equation of state becomes less than -1/3, recollapse does not occur, and the universe will inflate. So the recollapses keep on occurring, but as you hit -1, cross -1/3, recollapse is avoided, and then the universe enters the inflationary trajectory. This graph is impossible if you have singularities. If you have a singularity, like in the classical theory, even one cycle will not occur. The big crunch will just kill the universe. So, but in this case, even for highly unfavorable conditions, the inflation can start. So this was for the phi-square model. The main question is, how does this situation change for low energy scale inflationary models like the Starobinsky inflation? Now for the Starobinsky potential, we still get a non-singular evolution. But what we found is that there is a very little increase in scale factor in each cycle. Unlike the phi-square case, the cycles look almost identical. There is a very tiny increase in each cycle, which means that the pump is working, but it's not working well enough. And in each cycle, the field is just pushed little by little, and so on. But we found that compared to the phi-square model, the universe undergoes far more number of cycles and cycles of expansion and contraction. This should be contractions here, I'm sorry for a typo. And this was the work I recently did with Lucia Gordon and Boffili. So let us look at the equation of state here. I'm just showing a late time snapshot. So you can see that you start from some equation of state, and the equation of state is almost touching this line, the upper red dash curve, which tells -1/3. One may feel, well, in the next cycle, it will just cross it, touch it and cross it, but you have to wait sometimes for hundreds of cycles to occur that this line, this curve essentially crosses the red curve. And once it crosses this red curve, then that means it has crossed W equals -1/3, and the universe will then exit the phases of contraction and expansion and enter into the inflationary phase. So the main result is that for a large class of initial conditions, including highly unfavorable initial conditions, for the Starobinsky potential, loop quantum cosmology effects do lead to successful onset of Starobinsky inflation. But this is not always the case. Let me show you another curve. We found cases in which the universe keeps on executing various cycles, thousands of cycles of expansion and contraction, but not inflating. And this is exactly like really the worst case scenario, in which the equation of state, as you can see, like I'm just plotting in a very fine range, the equation of state is decreasing. So one is aware that, okay, that the pump is working in some way, but the pump is working so slow that it will take probably millions of cycles to reach eventually that equation of state of -1/3 and to avoid a recollapse and to enter the inflationary stage. So we found certain cases where inflation really does not start, and the universe executes cycles of expansion and contraction for thousands of cycles. So the question I have been recently understanding is, can inflation start in such cases, such extreme cases of the Starobinsky potential with some different mechanism? And this is the work I'm finishing. It will be up on arXiv very soon. And this is the work with Mason Mutaharfer, in which we have seen that if suppose you introduce a small amount of radiation in this model, and which is the idea of the warm inflationary scenarios. If you introduce a tiny amount of inflation as the initial condition, then it drastically changes the scenario. So let us look at the green curve here. So the green curve essentially starts from this blue curve. You can ignore this red curve here. Like, let us just focus on the blue and the green curve here. And what we find is in the blue curve, we find this is with some small amount of radiation present. And the green curve is a very similar curve I showed you in the last slide, where there are thousands of cycles occurring, but there is no inflation occurring. What happens is if you introduce a small amount of radiation, and this is with some cubic dissipation coefficient, which I've chosen here, then after some cycles, this additional dissipation caused by radiation causes the inflation to start very quickly. If you choose a radiation dissipation to be larger, much larger, then the inflation just starts out immediately, even just with after one bounce. And this is also shown in this plot below of the equation of state. The green curve is without any radiation, and therefore it just keeps on oscillating for a very long time. These are very extreme, unfavorable initial conditions for Starobinsky model. But if you have a tiny amount of radiation present, then the inflation just starts very quickly. The equation of state decreases rapidly within a couple of cycles, crosses -1/3 mark, and then the inflation starts. If you increase the dissipation, the inflation starts much more quickly. So essentially what we are doing by adding a little bit of radiation is making this pump more efficient. Radiation acts in pumping up this field further up into the potential much more rapidly. So these are the main results essentially, and I know like my time is probably also up. So let me just summarize. The main message which you can take from the talk is that loop quantum cosmology is essentially an attempt of understanding the quantization of homogeneous models. And with the assumption of homogeneity, the quantum geometry effects in loop quantum cosmology provide a glimpse of singularity resolution. You don't have to believe all these results, because essentially we are doing quantum mechanics on the quantum space-time. But a lot of work has been done in the last 15 years, and all the models which have been discussed so far, they point out towards this resolution of singularities. No model has been analyzed, and lots of models have been analyzed, in which the robustness of singularities resolution does not appear. There is no need of exotic matter. You don't have to introduce any violation of weak energy condition, and you do not have to tune any initial condition. It just occurs because of quantum gravity effects. So quantum bounce turns out to be a generic feature in all the simulations we have performed so far, and these simulations are performed with high performance computers, and including for highly quantum states, not only for sharply peaked states, in the presence of potentials, and also in presence of anisotropies. What I've tried to show you in the talk today is that the quantum gravity effects, as understood in loop quantum cosmology, can alleviate some of the problems of the very alien universe cosmological dynamics. They, in the sense, can result in a successful onset of inflation in low energy scale models in the closed universes. And there is a lot of ongoing work in linking loop quantum cosmology with CMB observations in various groups, and hopefully we will have unique signatures in next couple of years. So with this note, I will stop and welcome any questions.
Thank you, Param, for this very interesting talk, very complete, from the very basic introduction for everyone up to these last results, which are really impressive. It's been a very nice contribution to this meeting. So I'm sure that there will be some questions. We have time, of course. And I would like to, well, I think that my son wants to ask something. He wants water, okay. So if anybody has a question, please go ahead. I'm going to solve this little problem here. Okay, I'm back. I don't know if someone is speaking, no?
Maybe I can ask something. So, Param, what are the prospects to include, for example, anisotropic small perturbations near the bound and see what's going on with this kind of issue?
So first of all, like, we would have to understand how the anisotropies have to be included without perturbations, and a lot of work has been already done on that. So for example, we have shown already that for numerical simulations with the Bianchi-1 space-times, there is a bounce and the effective dynamics works very well. You get the singularity resolution and so on. We have analyzed in detail what kind of different types of singularities structures kind of form, not non-singular structures like I was mentioning about cigars and pancakes. Now these are non-singular pancakes, non-singular cigars. How do they change from one to another? There is a very little work done so far on perturbations with anisotropies included. And I think that is one of the main issues one has to address. That how do mostly the bouncing models, they suffer from the problem that as you are approaching the bounce from the pre-bounce universe, then the anisotropies increase tremendously near the bounce, and that can really spoil the features of the bounce and the features of the scale invariance and so on. So some work is being done, and on this, for example, like recently I've been working on trying to have some sort of a marriage of the aperiotic scenario of Steinhardt and Turok and the matter-bound scenario of Brandenburger and others with loop quantum cosmology, in which we can start from perturbations on others and then see them evolving through the bounds without using inflation. The next step would be to include anisotropies, the space-time anisotropies, like in the Bianchi-1 picture, and then see what is the effect on that. So the prospects are very bright. In next 2 years, I would say in next 1 year, one would get very good results. But as always, the field needs more young people like you. So I welcome every young person here to join whatever projects you can join, and let us try to get some results out.
All right, thanks for your answer.
There is a question in the chat. I can read it if you want. So Jose Navarro Salas is asking that you have assumed some small amount of radiation to enforce the jump to Starobinsky inflation. And he's asking if this radiation imprinting a deviation, if this radiation is imprinting a deviation from Vance-Davis vacuum state, assuming conventional inflation.
The short answer is that we are just assuming the radiation in the effective dynamics. So we have not done yet the quantum field theory of this model. We are just assuming the radiation in the Friedman equation and then analyzing the background dynamics. So we haven't essentially done the quantum field theory yet for this. Okay.
And I have a small question. I understand that the bounces are quantum mechanical in origin, or quantum gravitational in origin. But when you have the future expansion, and then the universe bounces again from a big volume to a small volume, so is this future bounce also of quantum gravitational origin?
That's a very good question. So for certain initial conditions, what happens is, and only for a small set of initial conditions, what happens is that you can have even the recollapses or the second turning point also of quantum gravitational origin. But in most of the cases, and especially the cases whatever I've shown in the discussion today, the universe quickly becomes classical after the bounce, and the modified Friedman equation just mimics the classical Friedman equation, and then those recollapses are all classical recollapses. So all the recollapses I showed in the plots today were classical recollapses. But yes, it is quite possible that if you start from a Planck size universe, then the modified Friedman equation is actually quite complicated. That's why I didn't show it. It has certain possibilities that the universe can be trapped in a quantum gravitational regime, never becoming classical, and it just keeps on cycling up and down. The recollapse also caused by quantum gravity, and the bounce also caused by quantum gravity effects.
Okay, thank you very much. Any other question in the audience? No, if not, then I would like to thank you again, Param, for joining us for nice talk. And I hope you can continue with us in the next talk by Fernando Barbero. Thank you so much.
Thank you. Thank you.
Thanks.